Alright, in 9.5, we're talking about rotating axes to get the general form of our conic equation. Now, this, the equations that go with this section and the calculations are fairly intense, I guess I'm going to say. So we are going to do the extremely shortened version of section 9.5. If you go back and watch the My Math Lab videos that go along with 9.5, you're going to see a lot more arithmetic work, a lot more calculations of terms that we're just not going to do. But we are going to talk about how to identify conics by looking at the equation and by doing, in one case, some really short calculations. Okay, identifying conics without completing the squares theorem. So that means that my term bxy is missing. So the terms that I have, so my term bxy is missing. So I can use this if there is no xy term. What this looks like, so the xy term is what we call the degenerate case. And so what this looks like would be ax squared, cy squared, dx, ey, and a constant f. And this is going to work as long as a and c are not both 0. One of them can be 0, but not both. And again, I don't have my x times y term. If I have an equation that is in this form, without that xy term, then I know I have a parabola if a times c is 0. Because if a times c is 0, that means I have only one squared term. And that's the case for the equation of a parabola. You have only x squared or you have only y squared. You don't have both. I know that I have an ellipse or a circle if a times c, those squared coefficients, are positive. And if that's true, then that means that both of those squared terms are positive. And that is the case for an equation for an ellipse. It is x squared plus y squared, or y squared plus x squared. And finally, I know I have a hyperbola if a times c, the product of those coefficients, is less than 0. So it's negative, because that means that one of my squared terms is negative. And we just finished working with our equations for hyperbola. And if you'll remember, it's either x squared minus y squared or y squared minus x squared. So let's put this to use for this first example. I have 3 different equations that I'm going to look at, and I want to identify what the shape of the conic would be for each of these 3 equations. For the first term, or for the first equation, I have an x squared term. I don't have a y squared. So that means if I multiplied a times c, those 2 coefficients, I would get 0 because my y squared term would be 0y squared. So that means that this equation will give me a parabola. This equation is going to give me a parabola. And it's an x squared parabola. So in fact, it's a negative x squared parabola, so that parabola would open down. If it were a y squared parabola, it would open either left or right. Alright, what about b? On b, I see that I have x squared and y squared terms. If I take a times c, if I multiply those coefficients together, I have a positive value. That means that this, this equation is going to give me an ellipse or a circle. It depends on, when I work on completing the square, it depends on what I come up with. But I'm going to have either an ellipse or a circle for this one. And then finally, for this one, I have both x squared and y squared terms. If I multiply the coefficients here, I get a negative because that y squared term is negative. So this tells me that I have a hyperbola, and my transverse axis is going to be parallel to the x-axis. So transverse axis is parallel to the x-axis because it is that x squared term that is positive. So that's quick and easy, right? That's mostly the type of thing we're going to focus on in this unit. Now this next one talks about finding equations when we rotate axes. We are not going to work through finding these equations, but we are going to talk about this just a little bit. Now in this rotation formulas theorem, I can find my new x-coordinate by taking x prime cosine theta minus y prime sine theta, and I can find my new y-coordinate by taking x prime sine theta plus y prime cosine theta. So you can see that I have switched orders here and I've changed operations. Okay, so if the xy axes are rotated through some angle theta, the coordinates xy of a point P relative to the xy plane and the coordinates of x prime y prime of the same point relative to the new axes are related by these formulas. Now I'm going to show you what this looks like. Again, I'm not going to make you do the calculations, but I'm going to show you what this looks like. So here I have, for example, let me get these lined up. Here I have a triangle, and it's centered and it's in standard position on my xy coordinate plane, and I have this point P with coordinates xy. If I rotate my axes, so if I were to keep center at center and I were to rotate the axes so that now I have this angle theta, this angle of rotation that I've rotated through, so that now x prime y prime is also at this same point P. So you see that my new axes are just rotated. I've kept the origin centered there, but I've rotated my xy coordinate plane so that that new point lines up, and I can rotate it back. What I'm looking at doing in practice, every conic we talked about was parallel to either the x or y axis, right? Well, what if it wasn't sitting parallel to an x or y axis? What if it was rotated some degree? So let's say this would be an ellipse that's still centered at the origin, rotated, let's say, through an angle of 30 degrees. Or we might rotate it through an angle of 45 degrees. That looks like that's about 45 degrees, correct? So I have these axes of rotation, x prime, y prime, that are offset from my original xy axis. Well, I can think about the equation for my conic. In this case, I've got an ellipse. It could just easily have been a hyperbola or parabola. But I can think about the equation for this conic in relation to the rotation, the angle of rotation for those axes. Now again, I'm not going to ask you to do those calculations because they get kind of intense. So we are going to skip expressing that equation in terms, but just notice that you're using trig, our trig calculations, our trig functions, cosine and sine of theta, based on that angle of rotation. How far did I rotate my conic away from the xy coordinate plane? All right, let's look at that next page. For this one, we are just going to talk about, again, this top, and we're not going to do any of our rewriting of equations, so we're just going to talk through this top part. If the angle through which to rotate is not given, then you can use a theorem, a double angle theorem, that will allow you to identify the angle to rotate in order to get that xy term out of your way, to make things simpler. So if you have this equation with this bxy term and you want to transform it into an equation in terms of x prime y prime without that x prime y prime term, you rotate the axes through an angle theta that satisfies cotangent to theta is equal to a minus c over b, where you're using a, b, and c as your coefficients to plug in here, as long as theta is an acute angle of rotation. Now, just for your information, FYI, anytime you were told through here to analyze the equation, that means you're going to transform the given equation so that that xy term goes away. And if that xy term has gone away, then you can go back to this method of telling what type of conic you have. Okay? Alright, since we're skipping the rest of this page, let's look at the last page of our notes for this section. Identifying conics without a rotation of axes theorem. So what if you do have that xy term? This one is going to include the xy term. What if I do have that degenerate case? No, except for degenerate cases, excuse me. If I do have that xy term case, well then I have ax squared plus bxy plus cy squared dx, ey, and f. And again, my a and b are not going to be both 0. Well, if I have, and we're focusing on a, b, and c once more, I know that I have a parabola if I work out b squared minus 4ac and I get 0. Now where do you remember b squared minus 4ac? Hopefully you recognize that as a part of our quadratic formula, right? But this is not strictly a quadratic because it's not just parabolas. That breaks it down to just a parabola. Okay, so we've got a parabola if b squared minus 4ac equals 0. We would have an ellipse or a circle if I calculate the value for b squared minus 4ac, and it is, that's wrong, less than 0. And it would be a parabola if I had b squared minus 4ac is greater than 0. So if it's negative, I have an ellipse, and if it's positive, I have a hyperbola. Let's practice this one time. This is the equation we're given where we have that xy term. So we can't go back to what we learned on the first page and say, okay, I can look at just a times c and those coefficients on those first terms and tell what I have. If I have that xy term, I have to look at more than the coefficients on the squared term. I have to look at b squared minus 4ac. Well, for this equation, a would be 1, b would be 3, and c would be negative 2. If I'm going to solve b squared minus 4ac, I have 3 squared minus 4 times 1 times negative 2, which gives me 9 plus 8, which is a positive 17, greater than 0. So this is the equation for a hyperbola. Now I would know that, I could have guessed that because my x squared is positive and my y squared is negative, but this xy term can throw a wrench in the works. It can mess us up and give us something that we're not expecting. So pay attention. Anytime you have this xy term, you have to evaluate b squared minus 4ac. If you don't have the xy term, then you can just look at how a, c relate to each other.